Okay, welcome everybody. Hi Daryl, thanks for being here in person. I apologize that it's on an afternoon, not an evening, as I usually would like to do, but I'm still in Europe and I will only be back in New York next week on Wednesday late night. So I will I will schedule another review session for the same time, again 1 p.m. Eastern Standard Time on Monday. For 7 p.m. my time, 1 p.m. your time. And on Wednesday, I have a travel day. I can't, unfortunately. I hope that Thursday, I will do 2 additional sessions. I will do 2 additional sessions, one on Thursday and one on Friday. So please, so this will be at 7 p.m. and I hope that's really good for everybody. So there may be a question on homework that is posted on Tuesday, and there may be questions also to the research notes. So, so the research notes, the deadline has passed yesterday. Most of you have submitted. You still have the availability to submit, but please understand that those that submit today, I will not take any points. Those that will submit tomorrow will have a reduction of 25%, as outlined on the syllabus. But please, I encourage you to just really accelerate work and make sure that you submit the research note following the instructions. Good. This being said, homework 2 has posted. Please make sure to review what is being asked for in homework 2. Homework 2 will be due on 7/18, and this will be a somewhat busy second half of the semester. So we have passed now, after exam 1, we have passed the first half. So now research note 1 was due, we have submitted that. And now we're really fully in more advanced analytics. And this will include the work on research note 2 that has been, that will be assigned on 7/11. So that comes online on next week on Monday. Class 12 will, as usual, already go online on Friday, so you can review this over the weekend. Please make sure that research note 2 is due on 7/22. So homework 2 is due a week before. Research note due is due on 7/22, and I believe that's a Friday. The problem I have with this is it's at the same time, pretty much at the same time due as the exam 2. Exam 2 will post on 7/18. That's again a Monday. And then we have research note due is due on 7/22. Unfortunately, I cannot give any extension on 7/22. So really make sure that time management, that you're on top of the time management for the research note, because this is the end of the semester and I need to grade this and I need to submit the grades ASAP to the registrar. So please make sure that you submit on time. Good. So this is basically what I meant to say about the housekeeping notes. We are now at class 10 and 11. Class 10 and 11 are 2 very important and fabulous topics. We are talking about maximum likelihood estimation for logistic regression, and you have the lecture recording to review on that. You have an outline of specificity and sensitivity and how that relates to thresholds. And this is the lab I quickly want to walk you through, because there are some caveats on that. And there's the ROC analysis, so the receiver operating characteristics curve analysis, which is essentially a tool to outline the diagnostic accuracy of a test or of a model. And this will then be very insightful on many accounts. So you can quantify predictive values, you can quantify sensitivity, specificity. You can also utilize an ROC curve and this balance between specificity and sensitivity to determine thresholds that you are, for example, employing on diagnostic testing or on diagnostic use of statistical models. And so this is quite an important topic, generally spoken. Class 11, and this is also a very comprehensive and very complex topic. So as you can see, these classes essentially are usually meant to be on a weekly basis, right? So you have quite a lot of work to do with 10 and 11. And 11 is a very complex topic discussing propensity score methods. And particularly here, you may have in your EPI classes, and I'm not super familiar, to be honest, on how propensity scores are now handled in the EPI classes. I know that back when I did my MPH, we did the EPI. In EPI, we mainly talked about a propensity score as a tool for adjustment, whereas matching, I don't think we did it in EPI per se. I think it was exclusively a BIOS620 topic. However, so matching of propensity scores actually getting increasingly popular generally in so in my world in medical research. It's getting increasingly utilized, and you find more and more publications that essentially use propensity score matching methods for good reasons, because essentially what you really can create here is a scenario to have these balanced groups, and you will be watching the lecture recordings, and we will be doing the labs. So you will see what this basically aims for. So just in plain words, you create two cohorts that should be considerably equally balanced in their covariates, that determine the outcome. So you're matching, and you're matching and creating these cohorts based on the exposure, and keep them separated as per the outcome. And this being said, you can essentially then match those groups and balance them between those two groups based on your covariate of interest, which we are doing on homelessness in our lab. So these are two very complex topics, and make sure to study them well, because they're very helpful and they will be part of the exam. So we have two lab examples, and they will be discussed in the respective lab. And I just want to walk again through the lab, the answer key that I have also posted. This is in respect to the fact that it's a very time-intensive course. I give you the answer keys as in the previous classes, but there are some caveats. So you will firstly here generate an ROC curve with the admit data. You fit the prediction model with admit as the response variable. You use interaction terms between GRA and GPA and the three covariates included in the model. You create a predicted probability. So you predict the probability for each individual in your data set. And you then create a threshold vector testing for different thresholds of probability of admission. And these thresholds essentially allow for you to calculate sensitivity and specificity. And I will outline in the code exactly what this is being done. It is also part of the lab. Please also watch the lab recording and see how the ROC curve is being generated. I will quickly walk you through that right now. Then we have lab 11. This is basically you generating a model as per the lecture model. And you're then being asked to create a different model, and you want to then assess the balance between the covariances of the various covariates in your matched samples. So you're comparing the means between two cohorts, and you are asked to visually inspect not only the propensity scores, but also the respective covariates. And then basically create a model that allows you to test the treatment effect of homelessness. And then you're being asked to create a second matching algorithm where you basically use a different matching type as nearest neighbor. And I will show you what that means. Good. So Daryl had indicated no questions, no specific questions to the lecture, and I have not seen any on the discussion board. So maybe you have not come yet to it. Please post questions on the discussion board. I remain responsive plus minus 1 day on the discussion board. So please post questions. And let's jump now quickly into our studio. So this is the answer key as it was posted. So you essentially also load again the Haven library. You load the admit dataset. I'm just minimizing here. Zoom. The floating meeting panels. Okay, so you're loading the admits data. Now we can actually let's close this up. So let's load it up. So essentially we have in the beginning, we're just opening the library, we're loading the data set, we're inspecting the data set. So here we have GRE, GPA, rank 2, and we have our predicted probabilities already from the class. We can create now a table of the outcome variable. We have zeros and ones, where 0 is no admission, 1 is admission. So we would now essentially create a model. And this model is GRE, GPA, rank, and the interaction term between GRE and GPA. So this is quickly done, and this basically is the same model as we have done already in the past. We're getting a model. We can now, with the predict function, model our probabilities out. So this will be done with this line. Type response means that it basically employs it based on the response, and it models out the probabilities. If you want to look how this looks like, you just have to look at the respective entries. With head, you always get the first 6. Please remember that. And you get the probabilities for each individual included and predicted for based on the model. You're creating then with line 51, you're creating a threshold object. So please make sure that you go through the code and make sure. And I found out that this is an older version where there was a mix-up between threshold and thresholds. Make sure it's consistent between threshold and thresholds. So the nomenclature plays a role because you will get an error warning if the object is not found because it's differently named. So with threshold, you're basically creating a sequence from 0 to 0.75 by an increment of 0.01. You get here with cents and specs, you get repetitive NAs that are basically presenting with the length of threshold, which is 76 entries, as you can see here. And then we want to then calculate essentially a probability. And this is calculated here. So we have the decision. This is basically P admit is greater than the threshold. This means that the probability is greater than the threshold that we have set. So we get here a 0 or 1, or essentially a binary response variable. Then we get here with CMAT. So if we're just setting threshold now to, just want to quickly walk you through the threshold of 0.5. So if we want to calculate now threshold I, okay, let's do this differently. Let's do threshold, let's do I equals 50. So now we get threshold. We have already created this object. So threshold is now, threshold is here already. We need to rerun this. So now we have threshold. is now this sequence of increments of 0.01. I equals 50. So now this should get us now for decision. We're getting, we get for decision, we get now an estimate of who of our population was actually presenting with a probability that was greater than threshold equals I. This would be 0.49. So now with CMAT, we're basically creating a table that is showing us decision 0, 260, and 102. So these are our false negatives, false positives. So we have 0, 0, that's a true negative. We have 1, 0, that's a false negative. Whereas we have with 1, 1, we have a true positive, and with 0, 1, we have a false positive. So essentially, when we use this knowledge now to translate it into a sensitivity and a specificity, we get here our counts. That's the sum of all the decision was 1 and admission was 1. These are our true positives. Whereas these are our false true negatives. We get 260 and 25. And this is being used here as our numerator for the specificity, and for the sensitivity, it's here numerator of D, which is our true positives. So we have now sensitivity of 0.19. So it basically creates this vector including all these respective entries. So now we have packed this in a for loop that essentially gets us now a for loop including all our estimates for sensitivity and specificity. This is essentially presenting with the threshold of a vector. So this is the cutoff. Cutoff is nothing else but threshold. Sensitivity specificity comes essentially from our estimates here, which are here nothing else but vectors. So these are the vectors that are just now included in the data frame. So now, after having this set up, we essentially now use this to calculate it as 1 minus specificity versus sensitivity. And this is the classical appearance of an ROC curve. So if we run an ROC curve, it will present in this format, where we basically have sensitivity, which is our true positive rate, and 1 minus specificity, which is our false negative rate. And essentially, this will show the area under the curve, which is a reflection of the diagnostic accuracy of a test. Of a test in this context is essentially our prediction model. And now what you're being asked is to, what you're being asked in the lab assignment is basically fulfilled by now. But what this essentially does here in the second line is you create a second model that essentially does not include the interaction term. You remember that model 1 includes an interaction term between GRE and GPA. So this is not contained in model 2. So here you basically are meaning to predict a second p-admit, a second estimate of the probabilities for all the individuals. You create again the threshold object, and you again create those two empty vectors for sensitivity and specificity, and you again running the same for loop. And by that, you establish now a second data frame that will allow for you now to create an ROC curve that essentially contains both estimate and models both diagnostic accuracy, both for the model with interaction term and for the model without the interaction term. So hypothetically, you could also add here a legend, for example. You could say that the blue line is the model without the interaction term, and the red model is the model with the interaction term. So this is essentially the lab for class 10. And please make sure to understand these lines, because that will be quite important for the research note 2. So we're doing, in addition to that, we do here likelihood ratio test, and we have done this already. So this is essentially comparing now both models, and not surprisingly, because we see that also here on the predictive and diagnostic accuracy of the compare in our ROC curve comparing those models, we essentially see that inclusion of the interaction term has not resulted in an improvement of our model, and it has not shown the interaction term to be significant. So this being said, it's actually debatable whether the interaction term should remain to be included. But I refer here to previous lectures on how you would test that. I'm just hinting on subgroup analyses, but probably not indicated given that the interaction term is not significant. So in addition to that, we have here also a calculation of the area under the curve. For this, we use the ROC-ARC library, and we're using now the prediction function. So the prediction function essentially allows for us now to predict based on our data from p-admit2, which are the model probabilities, to calculate now both AUCs. And this is the way how you would get the AUCs out of your predicted probabilities. And this AUC is the AUC that is consistent with the AUC that you computed here in your ROC plot with your mapped and estimated data from your 2 data frames. So this is basically lab 10. And I will also encourage you to also watch the lecture recording and lab recording and post questions to the discussion board. So Daryl, since you're on, do you have any questions on this so far, or did you have time to look at it already?
No, I haven't had time to look for at it yet because I was working on the research notes. So, but today I will definitely look at 10 and 11 because I know they're not due until a couple more days from now. So
yes, it's a Sunday evening.
Sunday evening, yes.
Yeah. So I have a working day on Sunday, and I will make sure to review the discussion board. So whatever questions come in, I can post recording so I can elaborate on the discussion board.
All right, I'm pretty sure now once I start to go and look at labs 10 and 11, I will be posting something to the discussion board.
Okay.
Yeah, because I know that you said that it's going to be on the research note something about those 2, the red and blue line, the sensitivity and the lines there. So I definitely want to get a better understanding about that. If you have time, can you go over it again a little bit?
I would like to move on to class 11, if that's okay. Going over it, essentially you will understand sensitivity and specificity by going through the for loop that is being. I encourage you to take this data here from the for loop, which is, for example, here on 88 and 98. And here, so a for loop basically utilizes I as the counter, and it goes from every entry in threshold, and it will iteratively conduct every line within the curly bracket. So this for loop will conduct all these executions, all these lines. And if you set I to an arbitrary number, so you say, I chose 50, which turned out to be the threshold of 0.49, which is a threshold for probability. And this is a probability that came from the model. So there was a prediction from the model, from p-admit. If you are using now your p-admit data as your raw data, and you set your threshold arbitrarily to 0.49, as an example, as I did before, you will see what each of these lines means. So the arithmetics behind calculating the sensitivity and specificity are fairly simple. So basically you have, for the specificity, you have the true negatives, and then you have all where your diagnostic test was actually 0. So the diagnostic test being the prediction of the model. So that would be defined as everything smaller than 0.49. Whereas your sensitivity would be defined as the true positives, which is D, where the decision was 1, the admission was 1, which essentially is a prediction, again, a prediction of the model, and whether this was indeed true. So this is how your sensitivity is defined. And the ROC curve essentially is nothing else but a graphical depiction of your sensitivity as a function of your 1 minus specificity, which is synonymous essentially with your false negative rate. So sensitivity, the true positives as a fraction of the entire positive tested, of those, no, wrong, true positives as those that really were admitted, versus the true negatives as those that were not admitted, but not diagnosed accurately by the model. So this is your false negative rate. So you see this relationship in the ROC curve. And by mapping that out, you basically get a feel for this balance between sensitivity and specificity. And this is important to know because, as I mentioned before, ROC curves and this balance between sensitivity and specificity is also important for you to understand the value of a diagnostic test. So if you, for example, and you did that in page 614, we talked about sensitivity and specificity. So if you need a test for community, since you're in community health there, if in a community you want to screen for any certain disease, like a first line of screening, you want a test that is higher in sensitivity. So it's more likely to actually test patients that have the slightest risk of disease. But when you want, so sensitivity is high. But if you actually want a test where you want to make sure that this individual is really truly negative, so this would be an advanced stage of testing. So let's say you have somebody where you, classic example, which has always created a lot of discussion in the medical literature, is, for example, mammography. So mammography as a diagnostic procedure that is done in women above a certain age to allow for early diagnosis of breast cancer. So essentially you're using a tool which is very sensitive and allowing for an early diagnosis of a possible tumor in the breast of a woman. But when it really comes to the decision of whether you really want to biopsy, for example, or you really want to, after biopsy, you come to the decision that you really operate, you need a test where you're very, very certain that this is indeed what you suspect it is. So specificity becomes more important at an advanced stage of diagnostic testing. So this is always, so you're factoring in at what stage are you diagnosing. So generally in community testing, you would choose something that is more sensitive, essentially, because you want to catch everybody in the community who has the lowest risk of developing disease. So that's why this threshold is important, because the test, at what level this test is being used, plays a role in terms of your what is driving your decision making. Is it rather sensitivity as well as it's a rather specificity. And there are various ways how you would employ this. So you can, rather than sensitivity and specificity, you can also use positive and negative predictive value, which is essentially a different arithmetic procedure. But you can also use, and this is often used, a marker that is computed as an interplay between sensitivity and specificity, the so-called Youdon's index. And Youdon's index is calculated exactly by creating a balance, a favorable balance between sensitivity and specificity. And it's one of so there are several tools how you would do that, but it's one of those tests that is being used to determine a threshold. And since all of these entries here are essentially nothing else but individuals that are plotted out in terms of their predicted probabilities and their sensitivity and specificity at different thresholds, this follows this outline. This curve is a depiction of using these different thresholds. So these thresholds are to be found somewhere on these plotted lines. And Youdon's index will help you to determine which threshold is the quote unquote most optimal threshold for your diagnostic test. So I hope that makes it a little clearer now.
It does.
I'm happy to hear that, because it's a super important decision process to essentially which threshold to embrace for your testing. And so the ROC curve is a very valuable tool for doing this. Okay, so I hope things are a little clearer. So again, please find an arbitrary threshold and just investigate whatever is in the for loop before you run the for loop. So the for loop is going over the entire spectrum of different thresholds, whereas you can arbitrarily just investigate it for one threshold that you're interested in. And you can, by that, see what the thought process between each of these lines are, in addition to what I just explained. Good. So today we need to also speak about the second lab, so we can't split it up. So I hope you all had a nice Independence Day, and that kind of blocked our first session. So let's quickly go into lab 11. And this is essentially using, again, the Haven library. So it is the RCT data that we had already analyzed for different purposes in previous labs. So we're factorializing race group and we're building a model. So we're including now in our analysis, we're including homelessness as our outcome variable. And we are essentially trying to do that because we want to create two comparable cohorts. One is homeless, one is not homeless. So just along the line of what we discussed in the lecture, which you will find in the lecture recording, we have now two equal groups that we are developing for homelessness. One is homeless, one is not homeless. And then we can utilize these for developing our final model, where we're actually looking at our treatment effect between those groups. So we're building now this logistic regression that essentially is giving us the probability for those that are homeless and those that are not homeless to be homeless based on these criteria, based on these covariates: age, sex, race group, and substance use. So this being said, this is our model. So we see here that age is not a predictor of homelessness, neither is sex, not significantly, but borderline significant with a p-value of 6.7. Race is here with white race associated with homelessness in a protective fashion. We have here substance use as being a quite strong predictor of homelessness. So what does this mean? So we have now developed a probability to be homeless based on the covariate we have at hand and included. So this being said, we essentially want now in a separate data frame, build up this probability scores with the accompanying characteristic homelessness. And we're doing this here with setting up this data frame, which is here PRSDF. We get now, so let's just quickly look at this. So now this is PR score, the probability score of being homeless. And here we have the accompanying individual feature for all of the studied individuals, whether they were homeless or not. So we have here probabilities for those that were homeless and those that were not homeless. So we are now basically bringing this knowledge all back to our RCD data, and we're just including this in addition. So this data frame is now the data frame we will be working with. So firstly, we're building the histograms, and we're showing now the distribution of these probabilities amongst those that were not homeless and the individuals that were homeless. So we essentially will see the distribution of these probabilities. And here, basically within the homeless, we have the probabilities shifted to the right, which is not surprising. But now we can match it with propensity score matching. We can now match homeless and non-homeless people, create subsets of those that were homeless and those that were not homeless that do match up. And by using this matching, we basically get a comparable distribution in two different groups, and we can utilize these two different groups to analyze them against each other. So we have library match it. We're taking out variables. So we're creating here the variables, and we're taking then out of the RCD data frame, we're taking those that are included in the variable object. So this happens here, and we have now an RCD no miss. Please note that RCD includes, in addition to that, here the command complete cases. Complete cases will exclude all NAs. So you basically get a subset of those that have complete data for all the variables you're interested in. So in the next step, you're basically creating now with match it, you're basically creating your matched data, which is, again, note that you include the model. You could also have used the model and just add the model name, but here you basically have a match it, you have the model that determines the probabilities for homelessness. You state here the method, which is nearest. So this is the nearest neighbor method. So I have you already started. So you can always in R, when you're interested in a function and you do question mark, match it, you get an explanation of what this function entails, what it allows you to do. It also gives you always overview of how to use it, and what the different options may entail. So here with method, you basically have different methods that you can use. So you can use nearest method, you can use optimal methods, you can use genetic matching, you can use exact matching, which is like the exact probability. So there are various approaches to do that. And you're being asked for lab 11 to actually not only use nearest neighbor, but also use a different matching algorithm. So I encourage you to really do this for the lab and submit an alternative approach. You have now, in addition, you have an outline how you visually compare these two groups. And this is basically shown here. Careful with plot mod match. You see the different QQ plots. And these are interesting to see because essentially you see here your over a set and here how it looks like when it's matched. So basically you see a comparison, and it's not a perfect match, obviously, because it's categorical data, right? With continuous data, you will see marked differences in the QQ plots, and you will see how the matching has improved in the distribution. But what you see when you compare here, for example, here in your control group, you see in OR, you see here quite a clustering of your of those where control and so homelessness and not homelessness does not agree well. You see in the match group that this has definitely minimized this non-matching data. So this is the problem that we have with categorical data. It's hard to match it. But this basically is good enough that you essentially can move on. And here in this chunk, 94 to 97, you basically create a data frame where you match based on mod match, which is your matched object from up here, mod match. You basically create now a matched data frame that allows you now to essentially move forward and run your actual treatment effect estimate on. So this is this line, and then we have the assessments of covariances. Now we can essentially plot this out, and you basically see that this has to some extent improved. It still has quite a shape that is quite systematic, which is a result of the model. But basically you see quite a decent number of matched pairs that essentially can be utilized for your analysis now. So now, for example, you can now with the tabular function, you can now compare age for these respective two groups. You can extend this analysis further and include additional covariates that you compare. And you can also do a comparison of the actual entries for different substance abuse or for racial groups. So you can do this here in this aspect where you compare then the proportions in the respective cohorts. So, and now, not yet last, but essentially you can now use CESD, which is your actual outcome that you want to quantify. You basically can now compare this between both groups without actually the need to additionally adjust your model, because you already have passively, indirectly adjusted by balancing your covariates between both cohorts. So if you look at summary fit 1, this will look now different and will be more reliable estimate than the overall adjusted model. So homelessness is now basically associated with your outcome variable. So this is an overview of your match data. You can now basically look at your match data. You can investigate it. And now you can look into your respective outputs. You can, with COEF test, you basically get a comparison between those groups. You see these differences between the groups as per the fit1 comparison, and you can now with COEF CI, you can formally compare it, and by also computing the confidence intervals. Basically allows you to get an overview of the variability between those groups and those differences. Okay, so this was lab 11, and this is propensity score matching. As said, the example is nice in terms of age. For example, you have a continuous variable that you're comparing. The categorical variable are a little bit harder to explain and to investigate, because categorical variables are somewhat very difficult to investigate in this regard. But you see here, for example, you see here this age, you see that the match group definitely goes low, goes increased towards the line of identity, which shows an increased agreement between predicted and observed, which basically allows you to kind of conclude that control units and treated units, so homeless versus non-homeless, are in better agreement in the matched cohort. So this is propensity score matching, and it's an elegant way to analyze data because it suddenly gives you an entire different possibility of how you can analyze your data. And it's actually, you can analyze propensity score matched data in a format that is kind of consistent with an RCT. So you can hypothetically, you can use the same regression tools that you would use for RCT analysis. Under the assumption that the groups are very balanced, you can use the same kind of analytic approaches, which makes it very elegant analytically. And for publications, it's a very elegant tool to actually present your data. All right, so this was Lab 11. Well, I'm looking forward to your questions. So Daryl, if you have a question, please chime in. Otherwise, I'm looking forward to your comments and thoughts and questions on the discussion board. I hope to continue the conversation.
Okay, Professor.
Yeah. All right. Any questions to that? Was it somewhat clear?
Yeah, it was somewhat clear. I definitely will be reviewing this lecture again.
Sounds good. Sounds good. Yeah, please post questions. Also watch the lecture recordings and the lab recordings. Let me know if you need any additional explanations. Happy to do so. The code should be quite easy to go through. There are some adjustments to be made, which I have outlined with threshold versus thresholds. So just don't trip over those. May give you an error warning at first, but you will get a handle on that, I'm sure. If questions, okay, please post them in the discussion board. Okay, great. Okay, as said, I will be on online a little bit this weekend. Happy to answer questions on the discussion board. If not, we're going to have as a compensation for now the time difference and these earlier lectures, I will make 3 evenings next week. So it will be Monday at 1 p.m. It will be Thursday and Friday at 7 p.m. Okay. All right, Daryl, thank you for joining. If no further question, I think we can conclude for today.
Okay, thank you very much, Professor.
You're very welcome. Have a nice afternoon and good talk soon.
All right, bye-bye.
Thank you. Bye-bye.